Can you hear me? Hi, hello, hello. Should lower the music a little. Can you hear me now? Okay, so let's talk about gravitational field. Gravitational field can be approximated as a perfect fluid. So that means we consider a gravitational field as a dust of particles, and each one of those particles have density, velocity, flux. So as if given a four-dimensional space, four-dimensional manifold, which is space-time, as those particles move, for instance, they will cross a surface. We can then calculate its flux, right? So given a certain volume, if you like time equals constant, then you have a cube. You have a cube of x, y, and z, and then you can calculate the density of the cube, of the number of particles inside. So, but remember, we're doing general relativity. So in general relativity, well, not even in general relativity, in special relativity, what we know is that there's dilation, there's time dilation. So you need to use Lorentz transformation. So that means, for example, in a cube, you usually have delta x times delta y times z. As a particle moves very close to speed of light, there is time dilation. So that means, for instance, if it's moving in the x direction, delta x will have a dilation, which is 1 over v squared, square root of 1 over v squared, due to Lorentz transformation. So you have to take that into account. So the density is no longer just the number of particles passing through a cube divided by the volume of, in that volume cube. There is a constant of 1 over square root of x squared. So that doesn't just account for that's the density. Then you can talk about flux, the number of particles passing through a particular surface, and that you also need to account for the time dilation, which is the Lorentz factor, which is square root of 1 minus v squared. And now you can also talk about momentum. You can also talk about energy. Why we can talk about energy? Because we have momentum, the form momentum. No, there no in regular physics, form momentum is just a number, but in general relativity, momentum become a four component. There are four components to it: p0, p1, p2, p3. p0 is energy, E divided by c. C is speed of light. Well, in general relativity, let's just call c to be 1. Speed of light is 1. Doesn't matter. So that means p1 is energy. p0 is energy. So now you can also talk about energy. Once you know the momentum, from which you have the mass, you have velocity, so you can calculate the momentum. And p1, p2, p3 are the direction of velocity in the x, y, z direction, as usual. And so that means you can calculate momentum and energy are both affected by the Lorentz transformation, which is that when you calculate, you have to account for 1 over square root of 1 minus v squared. And what you do is, once you have the energy, you can also calculate the flux of energy. What I'm talking. So what I'm trying to get to is that you can calculate the momentum. You can now define the stress energy tensor. what stress energy tensor does is it calculates the momentum, the flux of momentum going through a particular surface. So for example, you have T alpha beta. If alpha is 0, that means it's energy. It's the energy going through the surface. If it T1 beta, is the energy is the first momentum going through the surface, and so on and so forth. Now, what is surface? Remember, we talk about differential form, right? Surface is defined by differential form. So that means if you have or the one form defines the surface. So that's why we were talking about differential form all the time, because you can, once you have a differential form, you can now find the surface. So this is stress energy tensor, and it's using Einstein fields equation. So once you okay, so let's talk about I think I'm done with today. So we're getting there, but once we introduce the stress energy tensor, we just need to know a few other things before we can start talking about Einstein fields equations. Okay, so I'll do that maybe next time.